Okay, so we're going to jump ahead to chapter 8 in your textbook, and this is the chapter on measurement. Actually, it doesn't say that. Measurement. Sorry, my hands are all sticky, so I'm writing poorly. So measurement, this is one of our most useful units, and it is, I think the last three units are all going to be a little bit of a step down in terms of difficulty. There's quite a bit of algebra skills in those quadratics units and the radical functions and stuff. But these ones are kind of just stepping back. We're still going to ask a fair bit from you in terms of reasoning skills. So you're going to have to look at this and you're going to have to analyze somewhat complex questions, and every question might look different. So you really need to practice a fair bit, but a lot of this time you can probably common sense your way through at least what the question is asking, if not all the way to the answer. Make sure you do lots of practice. Make sure you're using class time effectively, because it's just going to be the two of you guys now for these last three units. Or we're done 5, 6, 7, 8. Yeah, last three units. Sorry. Okay, so let's start off with comparing and interpreting rates. So what is a rate? A rate is a comparison of two quantities. So if you want to compare one thing to another thing, like maybe how far did you travel based on how much gas did you have? So maybe gas versus traveled distance. That could be a rate. Or how much of something did you buy based on how much you spent? So price versus quantity. And these things are usually listed as a fraction. Sometimes they're listed with the semicolon, which is kind of a comparison, one thing to another thing. But oftentimes we do it as a fraction. So it's probably very often as a fraction, with the first thing on top and the second thing on the bottom. Or the other way around, depending on what the context is. A unit rate. We did all this in grade, is it 9? I think you saw this in grade 9. So this should be somewhat familiar. Or, oh, it's grade 8. Actually, you discussed this for the first time. So really, we're just expanding off what you do in grade 8 and doing some harder questions. A unit rate. A unit means one of. So a unit rate is a rate, the comparison of one thing to another thing, where one of those things is just one. So basically, comparison. Um, one quantity versus one of another is kind of what you do. So if you spent $1 on gas, how far did you get to travel? Or if you spent $1 on a certain type of candy, how much of that candy did you get to buy? Or how much toilet paper would you get for $1 worth of all these different products? So it's always one of something. Um, and usually we're going to start with some kind of fixed quantity, and then we're going to have to reduce it to a unit rate. That's very often how that works. So let's look at some examples. Natasha can buy 12 kilograms of turkey from her local butcher for $42.89. The local supermarket has turkey advertised in its weekly flyer for $1.49 a pound. There are 2.2 pounds in a kilogram. Which store has the lower price? So in order to compare the prices, we probably want to get a unit price for each. So right now we have an actual rate, which is if you buy 12 of them, you spend $42.89. The question is, do you want to know how much 1 kilogram of turkey costs, or do you want to know how much turkey you get for $1? I'd probably do 1 kilogram of turkey. That might be easier. So in which case we take our $42.89 price per 12 kilograms. of turkey. And all you have to do to turn that into a unit rate is divide them. Basically, we're going to turn the bottom into 1, so we're going to be dividing by 12. So what is 42.89 divided by 12? And the answer is 3.57 if we round. So that is dollars per kilogram. So that is our unit rate now. From our butcher, we're going to get, it's $3.57 per kilogram. Now we need to compare that to the supermarket price. So we know it's $1.49 per pound. So that's 1.49 per pound. And we want to know what that is per kilogram. So we need to turn this into kilograms. Any idea how to do that? This is a hard question at first. I think if you sat down and thought about it for long enough, you probably would get to the right calculation. But we want to be quick. We want to be really good at this. So we want to have a general strategy that we're going to use all the time for conversions. I call this the gauntlet. Hopefully you saw this in grade 10 and probably in grade 9 a bit. And in science class, you probably do it often too because you're always converting different things. So for the gauntlet, if we want kilograms on the bottom. I always put the ratio of what we actually want over here. So we want dollars on top and we want kilograms on the bottom. Now what we have to do is we have to get rid of the pounds because pounds isn't anywhere in this equation, so we need to get rid of it. Now which side would get rid of it? If I added pounds to the top or if I added pounds to the bottom? The answer is you add pounds to the, it's a little bit weird with this example. It's much easier with some other examples. But what you do is you add pounds to the top because then they're going to cancel. One on the top, one on the bottom, those pounds are going to disappear. So we get rid of pounds and we want kilograms is the way we're doing this one. Usually it's flipped upside down, we're doing it the other way. So how many pounds, what's our relationship between pounds and kilograms? We know there's 2.2 pounds in every 1 kilogram. Now if I multiply this whole thing, I'm going to end up with dollars on the top. This actually isn't dollars, this has nothing to do with dollars, but we do have dollars up here. So if we multiply by nothing, dollars are going to stay on the top. Our pounds are going to cancel, and we're going to end up with kilograms on the bottom. So all we have to do is multiply these quantities. So top times top, bottom times bottom for fractions. So what is 1.49 times 2.2? That is 3.278. And on the bottom, it's 1 times 1, which is just 1. So it actually disappears. So this is dollars per kilogram. That's how we got that. So which one is the better deal? We can find numbers all day, but if we can't interpret them, they're not good for anything. Would you rather go to the butcher and pay $3.57 per kilogram, or would you rather go to the supermarket and pay $3.27 or $3.28? We probably should have rounded, because we always have 2 decimals when it's money. And the answer is the supermarket. You'd rather pay less per kilogram. So therefore, the supermarket is the better deal at $3.28 per kilogram. Good. So finding 2 different unit rates and then comparing them using our reasoning skills. There were probably a whole bunch of different ways to do this one. I like to do the gauntlet every time because it makes conversions easy, I think. And I'll show you a lot more examples of that as we go through. But if you could have just common sense your way to get to this answer, that's fine as well. It can be a bit confusing though, so be careful. Okay, a long question. The gas tank of Mario's new car has a capacity of 55 liters. The owner's manual claims that the fuel efficiency is 7.6 liters per 100 kilometers. Before Mario's first big trip, he sets his trip meter to 0 kilometers so he can keep track of how far he drives. He starts with a full tank of gas each time, and when he stops to fill up the tank, he records his distance, assuming he tries to empty the car as far as possible. So, in which leg did he actually have better fuel efficiency? A whole bunch of numbers, not all of them matter. The ones that actually matter is mostly this. We want to find out how much distance for how much gas purchased in each leg of the trip and which one was better. So we actually don't care about this. We don't care about this. We're not assuming he used an entire tank each time. It actually says how much fuel he's putting in the car each time. This might not be a perfect way of doing this calculation, but we're going to treat it like it is. So, we can kind of, that's weird. He put more gas in the first time. Oh, I see. Let me just read this once more for clarity. I want to know whether this was the gas before the trip, how much gas he put in before the trip, or this is how much gas he had to put in after the trip. So each time he stopped to fill up the tank, he recorded the distance he had traveled and the amount of gas he purchased. So this is after. Okay, that's actually a great way of doing the calculations. I thought this was before, and then that wouldn't have been a clear indication of how much gas he actually used. Since it's after, we're assuming he started at 55, and then he had to buy 48 liters to fill back up, which means on that trip, he must have actually used 48 liters, right? And now he filled all the way back up to 55. He drives a whole bunch more, and then he has to fill up 32.1 to fill it back up. So over this second trip, he must have used 32.1 liters. So it is actually just that rate. Okay, so let's calculate each one. So in number one, we're going to be traveling. Do we want to do kilometers per liter or liters per kilometer? In this indication, it says liters per 100 kilometers. We could do that. Why don't we turn it into that same rate? Really, it doesn't matter. You could have done it either way. Kilometers based on 1 liter of gas, or number of liters it takes to drive 1 kilometer, or number of liters it takes to drive 100 kilometers in this instance. But since we have this in the actual question, let's actually calculate it per 100 kilometers. So we're going to have kilometers on the bottom, and we're going to have fuel on the top. So this is liters per kilometer. And we want the answer to be how much per 100 kilometers. So I actually like to write it as a rate. The one rate versus the other rate. And then it just becomes proportions. And we did a lot of this in grade 9. So hopefully it should be familiar. So how many liters does it cost to go 100 kilometers, if this is true? So you bring the 100 up, and then you have x by itself. So x should be 48 times 100 divided by 645, which is equal to 7.44 liters per 100 kilometers. That's not bad. So that's a little bit worse. Actually, or is that a little bit better? Yeah, it takes a little bit less gas, so it's a little bit better than what the fuel efficiency was indicated. Now let's try leg number 2. So exact same thing. He used 32.1 over 1,037, and that's how many per 100 kilometers. If you can't tell right away, this one's going to be the much better answer. This one's going to be far more efficient. Maybe it was on the highway the whole time. So the 100 comes up, 32.1 times 100 divided by 1,000 is 37. Is 3.095, so kind of rounding up, 3.10 roughly. That's rounded, that's rounded. And that's liters per 100 kilometers. Now this is way, way better. It's kind of weird actually how much better this one is. Makes me think there's a math error in here somewhere. But that's why I was being careful with how we interpreted these numbers. So I think it's right. It's just, this must have been all highway driving. The cars are more efficient when they're on the highway because they don't have to stop and start. So this is probably, oh no, that says for the highway. Huh. I don't know. Anyway, that's right. So which one was the more efficient one? Leg 2 was far more efficient. Good. You're going to have to do all these questions, but we're going to finish day 2 part first, and then I'm going to assign all the questions at once. Okay, opener question. This one's actually really fun. Read it over. Basically, what you're doing is you're taking a tap and putting each one of these containers under the tap, and the tap flows at a very even rate. So you can think of it like a really slow stream going into each of these containers. Which graph fits which container in terms of how high the water is? Okay. So pause, take 2-3 minutes, try and make your guesses. Okay, the two easiest ones are probably the flask and the drinking glass. The flask, if the water's flowing in here, it should start slowly. It takes a long time to fill up the bottom, but then it gets faster and faster and faster. And that should be B. Starts slowly and then gets faster and faster and faster. Now, the drinking glass, on the other hand, does the complete opposite. As the water's flowing in, it's going to start pretty quick, and then it's going to go slower, slower, slower as it gets up there. And that should be D. D is the drinking glass. And now we have two more. They look like they're kind of straight up and straight up. So we can't actually tell based on the rate. So what we have to look at is how quickly the water is going up. Which one would fill faster? And that should be the graduated cylinder. So the height, and the actual height numbers is much taller as well. So the graduated cylinder is the faster one. And the beaker should be the slower one. Good. So we're comparing rates of change in graphs now. And rates of change are usually the slope. So let's try a couple questions. These ones are actually pretty quick. If this was a graph of how far an ATV was away from something, distance from your cabin. So you go up to the cabin and then you go on an ATV trip. So you started right at the cabin, and then you traveled away, you stopped, you traveled away, and you returned. Hopefully we can interpret that pretty good. Over which interval did the ATV travel the slowest? It depends whether you want to call this the slowest. This is technically 0, and I probably would. So I would say from 30 to 40 seconds. Sometimes we use little brackets for that. A square bracket means including the number. A round bracket means not including the number. So from time 30 to time 40, he was traveling the slowest. When was he traveling the fastest? This part right here is probably what you're going to look at first. Now it's a very steep. He is traveling quite fast, but that's actually not when he's traveling the fastest. Which leg is he traveling the fastest in? That should be this last one, actually. He is booting it home super, super fast. So he's going at a pretty good speed away from the cottage. Then he really, really rushes back. So the fastest he travels is actually from time 60 to time 65. This thing did not say direction. It didn't say when is he traveling the fastest away from the cottage. It just said when is he going the fastest. So that is whatever part of this line is the steepest. And that's definitely the last part. When does the ATV start to return to its starting position? Starts to return at 60 minutes. And when does he get home? Home at 65 minutes. He travels 5 kilometers in 5 minutes. I guess that's 1 kilometer a minute. So that's 60 kilometers an hour. That's pretty good. That's a fast speed for an ATV. Very, very fast, but doable, I think. What does the horizontal segment of the graph represent? So what's actually going on here? He rests. He either rests or travels horizontally to the cabin. His distance does not change. So we can't actually perfectly tell what's happening in that point. All we know is he's not getting closer to the cabin and he's not getting further away from the cabin. So he could be traveling parallel to it, or he could be stopping and just resting. One of those two things. Okay, so that's interpreting slope. Pretty straightforward. In order to fill in the answers to these questions, what you are actually doing is analyzing the slope of the graph. What is the slope? It is the rise over the run. It is the change in y over the change in x. We have 3 different formulas. Hopefully you remember all 3. Rise over run, change in y over change in x. And the last one, this one might be hard to remember. y2 minus y1 all over x2 minus x1. And all those mean the exact same thing. You take your second y and you subtract your first y. That's your change in y. That's how much you went up by. Second x, take away your first x, is your change in x. That's how far you went to the side, how far you're moving sideways. So how far did you go up divided by how far you went sideways. This is also the rate of change of the graph. So if you're thinking about it in the graph, it's the rate of change of something. And this happens in word problems all the time. If you're talking about you earn $20 for going into work and you earn $5 per hour. The slope of the graph you produce is just going to be the 5 because that's your rate of change. It's 5 per hour. The 20 will never ever change. It's always going to be the same. So that would end up being something like y equals 5 times the number of hours you work plus 20. So that is your slope there, which is your m value in y equals mx plus b. Whatever your m value is your slope. Lots of stuff to remember from grade 9 and 10. I think this is largely grade 9 actually, so hopefully it's pretty common sense for you guys now. Example 2. This one's fun. I always like drawing the graphs. You should maybe try it on your own first. A car travels at 60 kilometers an hour for 30 minutes, increases its speed to 85 kilometers an hour, stays there for 10 minutes, then decreases to 30 kilometers an hour for 2 minutes. Draw a graph to represent the situation. So what should our scale on the bottom be? That's definitely going to be time in minutes. And on the top, it's going to be distance, not speed, distance in kilometers. Okay, 30 minutes, another 10 minutes, another 2 minutes. So 30 should be most of the way. So 10, 20, 30, 40, 50. That should be enough. We're just doing a sketch. Hopefully you have a ruler though, so you can do it a little bit better than I'm going to do it. Total distances. So 60 kilometers an hour for 30 minutes means you're going 30 kilometers up. Then 85, so maybe another 40 kilometers up. Maybe another 50, so maybe up to 50 kilometers or something like that. I'm not sure exactly, but I think that should be fine. So we're actually going to draw a straight line from time 0 till time 30. And at time 30, how high should we be? 60 kilometers an hour for 30 minutes means you're only going half that distance. So you're going up to 30. So at time 30, going up to 30. Draw a dot and connect them with a ruler. I don't have a ruler right now, but I can try and use the straight edge. Something like that. Now, for the next 10 minutes, increases its speed to 85 kilometers an hour and stays at that speed for 10 minutes. Okay, so for the next 10 minutes, he's going to travel another, what's 1/6 of 85? Because 10 minutes is 1/6 of an hour. So 85 divided by 6. We're going to add another 14 kilometers based on that. If you had to estimate it, you could estimate it, in which case it's just going to be a little bit steeper. But we could actually calculate it. So add another 14, so we should go to 44. So it ends up being a little bit steeper. And connect those dots. And then goes back all the way down to only 30 kilometers an hour for only 2 minutes. So that's going to be half of this slope. So it's going to be pretty shallow and only for 2 minutes. I think I'm just going to guess at this one. It's going to be pretty slow and very short distance. Something like that. Good. Distance, time, and this is your car trip. Something like that. Easy, easy, you guys say. This is so much better than doing it with the 20-1 units. Example 3. The only problem with this unit is there's a lot of different types of questions. So even if you've tried the ones in this worksheet, doesn't mean you're ready for the test. You have to actually try lots of homework questions to make sure you're ready. Anyway, let's try and finish this nice and quick. The following table shows the amount of greenhouse gases emitted by fossil fuel from 1990 to 2006. So we're going, it's not going up by every 5 years. It's weird time scales. 5 years, 5 years, 3 years, 3 years. The amount of fuel per year, does it say? I assume this is per year. Graph the following information on graph paper. Okay, so we need to create a little graph. There's graph paper at the back of the classroom if you want to use that. I'm just going to do a sketch of it. You guys can do a little bit of a better graph, hopefully. So this is year. And we're going to start with 1990. And then we probably could put ticks every 5 years, and then we'll have to just put these ones in between them, maybe. So 5, 10, 15, we need to go about 20. So 4 big ticks. 1, 2, 3, 4. So 95, 2000, 2005, 2010. 19. I guess I'll put the whole number there. And then how much fossil fuel in megatons? So this is megatons. And our numbers are way up in the hundreds. Now we need to make one big question for ourselves. Should we start at 0? Or should we do the squiggly line and start at 100? Now both is good for certain things. If you start at 0, it's going to be good for showing how much above 0 it is. It's going to be good at showing a real scale of exactly how much we're polluting. So it's very good for that. But what it's bad for is showing how much it's changing between the years, because all the numbers are going to be way up here at the top. It won't show the change between the years very well. If we skip it all the way down to 100 right here and put it up from 100 to say 200, then it will show the changes between the years very well, but it won't show how much we're really polluting every single year. So we need to make a judgment call. Which would I do? I think I care more about how much it's changing between the years. So I think I would do a squiggly line. So that's what I'm going to do. So we're going to go whoop, whoop, whoop. And call that 100. So we're only going to be looking at from 100 to, say, 200. So we need 5 ticks. 1, 2, 3, 4. And I'm off my graph a little bit for 5. So 120, 140, 160, 180, and 200 at the top. So megatons, it's actually emissions, greenhouse gases. Measured in megatons. It's not just megatons. Megatons isn't a thing. It's the amount of greenhouse gases we're emitting in megatons. Good. Then we just need to plot our points. So at 1990, we're just over 100. In 95, we're at 127. In 2000, 151. That's 160, 151. 2003, 161. On graph paper, this would be far more accurate. And in 2006, we're at 158. So it comes back down a bit. Do we connect the dots? If we're doing it with dots, you could have done it with a bar chart, but it wouldn't have been so great with a bar chart. I would connect the dots. I think it's probably fairly linear between these dots. It's probably a reasonable guess. I think it's reasonable to say in 1997, it was somewhere between these two dots. It was probably going up consistently. So something like that. Good. During which period was the fuel amount emitted increasing at the greatest rate? When was it going up the sharpest? When were we getting the most polluted the quickest? And that should be right at the beginning, I think, based on this graph. If your graph's more accurate, maybe you have a different answer. But I think it's from 1990 to 1995. And let's actually calculate it. So let's not guess. The slope in this case is going to be change in y over change in x. I'm going to use that formula. So what was the change in y over that time? So our y values are up here. How much did that change? Well, the answer is 24. The other way to do it is y2 subtract y1. But yeah, 24. How long did that take to happen? What's the change here? 5 years. Which is 4.8 megatons per year. we were going up at a rate of 4.8 megatons per year. And if you wanted to check your answer, or if you two look really, really close, you could maybe try another one as well. The second gap also is 5 years, so the question is it more or less than 24? 51 minus 27 is actually 24. It's the exact same. So my graph wasn't very accurate. This one has the exact same rate of change. Why don't I try this one then as well? So that was M1. M2 is also 24 over 5. M3, what's our change here? Well, it's 10 over how many years? 3. That's also equal to 4.8. What's 10 divided by 3? Is 3.3. So actually it's from 1990 to 2000 is all the same rate at 4.8, increasing by 4.8 megatons per year. Then it slows down, and then I didn't even check the last one because the last one's actually a negative number. It goes -3 over 3 years, so it's going down by -1. So it's definitely not the last one. Okay, 36 minutes. Not too bad. 2 sets of homework questions, and you have about an hour to do them. So please try lots of questions and come and ask me if you need help, and good luck.